Hello class, welcome to Chapter 8, Confidence Intervals. Let's begin with some basic concept ideas. The idea of confidence intervals is to be able to estimate information about the population with a certain degree of confidence. For that, we need to have an idea of point estimate, confidence interval, and sample size. Okay. So I will just quickly define these things and then we will look at it, okay, individually. Point estimate. You know, point means a single value, right? A single spot. So point estimate is a single value that is used to estimate a population parameter. Remember, when I say parameter, I am talking about finding the population proportion. Again, think of proportion as a percentage. So I'm asking, is 5% of the population, are folks wearing contact lens? So then I'm trying to find a percentage of the population, a proportion to make my claim. Or I could be talking about an average, which is the mean, right? What is the mean wait time at a drive-through restaurant? So we can have questions about the population and we answer those questions by using certain measurements. The measurements can be proportion, mean, sometimes standard deviation, and so on. So this point estimate is a single value to talk about the population parameter. And there we have the sample proportion. It uses, the book uses the two kinds of symbols, p hat or p prime. So feel free to adapt to what the book is using. Sample proportion, p hat, is the best point estimate of the population proportion. And the notation for this is just p, okay? Both are lowercase p's, the sample and the population, but the sample has the p hat or the p prime notation, and the population proportion just has the p. So if I want to know what is the mean drive-through, not in this case mean because it's proportion, let's say, do 60% of the population choose the drive-through lanes at a restaurant? So if that is the question, now that's for all the people who drive through there, right? That's the entire population. They're trying to make an estimate based on that. So the question is for the entire population, do 60% or more of the population drive through to use the drive-through lane for that restaurant? Now for that, I can collect a sample, a smaller group of people who use the drive-through lane in that restaurant and see how many use that drive-through lane in a day, in a month. It can depend on how my study is. And then if I found the sample proportion to be 60% or more, then that I could use that information as a good point estimate of the population proportion. Okay, that's what this means. So p hat, the p hat is coming from the sample, right? So p hat is the statistic that targets p, which is the population parameter. Okay. So I'll give you an example here. So I'd like to go to the slide. A Gallup poll was taken in which 1,487 adults were surveyed, and 43% of them said that they have a Facebook page. Based on that result, find the best point estimate of the proportion of all adults who have a Facebook page. So if you think about this, the proportion of all adults, so this is to do with the population. I know it's a population proportion because that's the whole story, proportion of all adults. But then they did not go around talking to all the adults. They surveyed 1,487 adults. And of them, 43% said that they have a Facebook page. This 43% comes from the sample, okay? Sample proportion. Remember, percentage or decimal equivalent indicates proportion. So sample proportion, we're using p hat or p prime, any one of those notations, and that is equal to 43% or 0.43, right, in decimal, or you can say 43%. So what we're saying is this p hat itself is the best point estimate, because that was the next question. What is the best point estimate? And the sample proportion is the best point estimate of the population proportion. Okay, so then we come down here. Oh, well, apologize. Have a quick cut here. Okay, back on track. So we have for that example, we can say p hat is 0.43 is the best estimate of the population proportion. Next, we talk about confidence interval. A confidence interval or interval estimate, that's another name for it. So I just say also known as interval estimate. Okay. It's a range of values, interval of values, used to estimate the true value of a population parameter. So as we mentioned, we do not know about the population often. We don't have information about the population, but we can use these estimates, to help us land as close to the true population parameter as possible. So we provide a range of values. We say the true population proportion is likely to fall in this interval, and we are a certain level confident. So that is the confidence interval we're talking about. And it's sometimes abbreviated as CI, confidence interval. Okay? So I'm just going to give you the details here, and then we will look at how they play a role in developing that interval. Okay? Right now, we're just looking at the definition. The next one is confidence level. Confidence level is the probability 1 minus alpha, okay, So it's usually like 0.95 or 95%. That the confidence interval the one that we just discussed, right? So it's a probability 1 minus alpha that the confidence interval actually does contain the population parameter. Okay. So this is also known as AKA degree of confidence or the confidence coefficient. And its abbreviation would be CL, confidence level. So I want you to understand again that confidence interval gives you the range of values. Confidence level talks about the probability, the percentage, the probability that the confidence interval, right, actually does contain the population parameter. So I'll give you a kind of a table here. Okay. So let's say most common confidence levels, CL, and their corresponding values of alpha. Okay. It's kind of a table. So if I want to use 90% confidence level, its decimal will be 0.90, right? Then the corresponding alpha will be 0.10, the remaining 10%. And if my confidence level is 95%, 0.95, then the leftover, right? We're 95% confident, so the error could lie in the remaining 5%, right? So your alpha is 0.05. Then you have 99%. So you're making it stricter and saying, well, the room for error here is 1% kind of a thing. So your alpha is that 0.01. Okay? So that's a relationship between confidence levels and the alpha value. Now, suppose we say, I gave you this information, say confidence interval, right? It's a range of values. So I said 0.405 less than P less than 0.455. P, stands for the population proportion, right? So if you simply were to read this mathematically, you'll say the population proportion is between 0.405 and 0.455. How do we interpret this? Okay? So I'll just write here, interpretation. You can interpret in so many ways, so I will point to the correct way of interpreting this. So we will say, we are, say this was for a 95% confidence level. We are 95% confident that the interval from 0.405 to 0.455 actually does contain the true value of the population proportion P. See the language. Okay, this is the correct way to explain that interval, the confidence interval. We're saying, and it depends on what level we set. If we set it as 95%, then we're saying that we're 95% confident. If we found this range of values to be good for 99%, then we'll say we are 99%. Okay, so we are 95% confident that the interval from 0.405 to 0.455 actually does contain the true value of the population proportion. We're confident that the true value will lie in this interval. Okay, now we can also interpret it wrongly like this. So making it very, very clear here, wrong. There is a 95% chance, because of the probability, we immediately say chance. No, this is confidence, not chance. There's a 95% chance that the true value of P will fall between 0.405 and 0.455. Note the difference in the language. Correct interpretation says we are 95% confident that the interval contains the true value. But the wrong version says, oh, there's a 95% chance that the true value will fall in between. So that is very different from the correct version. Okay. There's also another wrong version. You could say 95% of the sample proportions will fall between 0.405 and 0.455. That will be incorrect again, because nowhere have you mentioned in both the wrong versions, right? Nowhere have you mentioned about your confidence, because this is 95% is not the probability of this happening or not. It's a probability that indicates the confidence level. So you have to use the language that involves confidence. So we are 95% confident. Okay, I want to make that very clear so we understand what that means. Okay, so a confidence level of 95% is actually a process that in the long run will result in the confidence interval limits that contain the true proportion 95% of the time. Okay, so if you had 20 different samples, then you're basically saying, well, 19 out of 20 times, right, that sample will contain the true population proportion, okay, the intervals that you obtain from each of those samples. Okay? So if you had 20 different samples, each sample, you can build a confidence interval. Okay? And we want to make sure that that confidence interval contains the true proportion. So we have, let's say, you had, 20 sample. Let me see if I can show this to you quickly here. Look at this the screen here. So if you had 20 samples, so look at these red ones. So these red ones are 20 of them, right? So 1, 2, 3, 4. So there's 19 reds and 1 green, okay? So if you look at the 19 values, so it's 0.45 and 0.55, right? In between is, say, the actual population proportion, P, the P without a hat. So P is 0.5. So then that indicates that all these sample intervals, right, between this to this and here to here, all of these have that 0.5 on them. And one of them did not have that. This particular green sample had an interval, confidence interval, that did not contain the population proportion 0.5. So what we're saying is, we are able to say this process will work in the long run, that we are 95% confident that the true proportion will actually lie in this. So in this case, when I say 95% confident, it's 19 out of 20 times, right? So, so you are basically trying to understand this as a process that happens in the long run, that you are able to speak with confidence about the interval actually containing the proportion. Okay. So then how do we measure this? Well, there are other things we have to, that we have to consider. We have something called critical value. As the name says, critical value is critical because it's in the borderline. So I'll just say it's a number on the borderline. Separating sample statistics that are significantly high from those that are not significant. Oh, sorry, sample statistics that are significantly high or low. It could be one of these. It could be significantly high or significantly low from those that are not significant. Well, again, if you remember, we said, well, if it is in the normal curve, right? We said if it is one standard deviation this side and one standard deviation that side, we are good. If it's two standard deviations this side, two standard deviations that side, we're still good because we have 95% of the population of the values contained in there. But anything beyond two standard deviations, so let me give you a quick diagram here. And then we said if I had, this is the mean, right? And this is mu minus 2 standard deviation. And this is mu plus 2 standard deviation. This is 1 standard deviation. And this is 3 standard deviations. And then we said anything that is beyond here and beyond here, right, means something is unusual, okay? We went over this early in the course. If anything is unusual, it means it's significant. Here, we use a particular cutoff, okay? The critical value here is a specific cutoff. The symbol for that is Z alpha over 2, because remember, it is all about the alpha, because we are setting the confidence level, the confidence interval, so it can't always be mu plus 2 sigma or mu minus 2 sigma. It just depends on how stringent we want to keep the significant area, right? So for that, if it is 95%, there is a certain borderline for that. If it is 99%, the borderline changes. So that's what we're trying to utilize here. So Z alpha over 2 is the critical value. And we're using Z scale, not the X scale, right? Because that's a standard version, standard normal version. So Z alpha over 2 is the critical value that is a Z-score with the property that it is at the border that separates alpha over 2 in the right tail. Please remember that, okay? Because you do have two tails here, right and left. We would focus on the right tail. of the standard normal distribution. Okay, so then I have to adjust this graph to match with the z-scale. So remember, if it was, that's z equals 0. If my confidence level was 95%, we go back to the chart. Let's quickly go back to the chart. 95%, then my alpha is that remaining 5% or 0.05, right? So what this means is my 5%, so that would be meaningful here, right? So this yellow shaded region must be the remaining 5% because inside this whole area, right, this whole thing is 95%. You with me on this? So if this is 95%, the remaining ends, tail ends, must take up the 5%, right? So this is 95%. So this is 5% together, the yellow. However, they are equally shaded on both sides, right? So then that 5% has to be divided into two parts. So that is 2.5% here and 2.5% here. Does it make sense? And 2.5% is 0.25, 0.025, and this will be 0.025. So what basically happens is you are looking at, come down here. If CL is 95%, alpha is 5%, right? And you need to divide this alpha into those two regions, one for the left and one for the right. And because they're equal regions, you need to do alpha over 2. Alpha over 2 gives you 2.5% for each tail, right? So if you're only focusing on the right tail, then you got the 2.5%. Now, if your CL was 99%, then alpha will be just that 1%, right? And that alpha has to be divided into two parts. So that's going to be 0.5%, because it's 0.5% for each tail. And likewise, if your CL was 90%, alpha is a huge chunk, so that's 10%, which means alpha over 2 will be 5% for each tail. Does that make sense? So to kind of generalize this, I noticed that, we noticed that each time we find the alpha, we have to do alpha over 2. And that is what this definition says. This definition says, well, z equals 0 is the middle, the mean position. So then if I had z alpha over 2, right? Alpha over 2 is the area. Remember, that's a percentage. That's the area. So if I had this area, the yellow shaded region known, we can do inverse normal. Remember inv norm in your calculator. And also in our table, when we did the tables, we looked at the body of the table in the z-scores, located the area, and then found the corresponding z value from it. And so that is the idea of alpha over 2, because you are dividing the alpha into the two parts, alpha over 2. And so on this side, this would have been a negative z alpha over 2. That's why we're not worried about the left half, because we're just focusing on the right z. And this also would be alpha over 2. So together, alpha over 2 adds up to alpha. But then we are only focusing on the right tail of the standard normal distribution. Okay with that? So that is the border line that separates the yellow shaded region, which is a significant region, the critical region, from the non-critical region. So we'll do an example to kind of understand that. Find the critical value z alpha over 2 corresponding to 95% confidence level. Well, we just revolve around 95, 90, and 99% because these are commonly used. You are free to use any confidence level technically, but these are the most common ones, so most of the examples will use these ones. Okay. So you can go ahead and use the calculator to help you with using the inv norm, or you could use the table to come up with this. You can use technology or the table. Okay. So first, let's understand that confidence level is given to be 95%. This implies alpha is 5%. This implies you have to divide the alpha into two tails. So you just are focusing on one of the tails, the right tail. So alpha over 2 is 2.5%. But remember, you have to, if you're looking at the table or if you're using technology, you have to write this in decimal form. So that has to be 0.025. Okay. Now, if I were to again shade this, remember my z alpha over 2 is only for the right tail. So this is the area that measures to be 0.025, right? This is 0.025. But if you are using table or technology, it is automatically going to give you the cumulative area from the left, right? So it will give you the cumulative area from the left, for which you have to do 1 minus 0.025. Okay? Since the table, I mean the z-score tables, right? Since the table, and technology in this case, measures the cumulative area from the left, we use 1 minus 0.025 to find the cumulative area from the left, which is 0.975. Okay. Now use 0.975 to find the corresponding z value. Okay. So I'll say 0.975 corresponds to z equals 1.96. Okay. I want you to take a moment to check that quickly. You can pause the video at this time and then quickly check that. So I can kind of show you here where I have the table. So you are looking at, oops, wrong screen. You're looking at 0.975, right? And so that is to be found in the body of the table, 0.975. Okay, you have that exactly here. Can you see that? I have kind of circled it. Maybe I'll try to highlight it. Right. So 0.975. Then see what it corresponds to. So go all the way here, 0.9, and then go all the way here to see what it points to. So then you have one, oops, that was a bad color. Okay. You had 1.9 here and 0.06. Kind of bring them together because it's 1.9 plus 0.06, which is 1.96. Right? So that's what you should get, and that's what we got. So the z alpha over 2 in this plot actually gave us 1.96. Now if you, and we're only looking at the right tail, right? If it was the left tail too, that would be a negative 1.96. Because they are symmetric, we find it sufficient to find just one tail. Okay? So then we come back and we say the critical value of z alpha over 2 is 1.96. Remember, this borderline is 1.96 in the z scale, and this can change if your confidence level was given to be a different value, isn't it? So that is the reason why we just give in general as z alpha over 2 as the borderline. Okay. So we also have tabulated common critical values because, as I mentioned, we use those 3 confidence levels as the common ones. So why not have critical values calculated for those specific ones? Critical value Z alpha over 2. You have to write it as a suffix, you know, as a subscript, so that it's not in the same level as Z. All right, so now I have 90% confidence level. Remember we said alpha was the remaining 10%, so it's 0.1. And if you use the table again, you will get 1.645. We just saw that for 95%, we calculated ourselves. 0.05 is the alpha, but alpha over 2, and then finding 1 minus the cumulative. To find the cumulative area from the left, you had to do 1 minus that alpha over 2, and then use that information in the body of the table, and we got it to be 1.96 as the Z value, the Z score. Remember again, Z score is on the Z scale, like it's there. It's like your x-axis, but instead of x-axis, it's your Z-axis, right? So you can have your Z scores going on the positive and on the negative, just like a number line. The middle value is 0, and then like you have middle value is 0, and then you can go 1, 2, 3, and so on, right? In this case, it can't be 1 there because it's 1.96. So you have your Z values just like the number line, but your area or percentage cannot be, if it's in percentage, it cannot be a negative and cannot be more than 100%. If it is in decimals, it cannot be negative and it cannot be more than 1, right? So that is how you have to take care of how you present your answer. So alpha is always a probability, so we always write it in decimals, and of course it does not exceed 1. When it is 99%, the critical value is pushed even further to 2.575. Okay. Then we talk about margin of error. Okay, so books can use different notations for this. So please understand how they are calling this. Margin of error could be, the notation could be simply a capital E, or ME for margin of error. Right. So just see what the book says. It is the maximum likely amount of error, right? Margin of error is the maximum likely amount of error, because it's in the margin, right? That's as much as it can go. That is what we're saying, the maximum error of estimate. For that reason, it's also known as maximum, I'll just say AKA, maximum error of estimate, because you're estimating. Remember, we don't have full details about the population, so whatever you're doing with the sample will be a best estimate at best, right? So it can only be an estimate, it can be a guess that we are trying to moderate so that it is reliable to use to some extent. And what is that extent? Well, we're saying, here's the margin of error. This is the maximum likely amount of error we can accommodate so that we can be confident about what we are projecting. Yeah. So how do we find this? There's a formula for this, okay? So E is given to be E or ME Z alpha over 2 times P hat Q hat divided by N. Okay? And if they used prime, then it will be P prime Q prime. So I'll write that also. Okay, I think they should stick to one notation so that we don't keep changing the way it is, but well, we can only make suggestions. It's been in use for some time now, I think. Okay, this is called the critical value, right? Z alpha over 2 is the critical value. This thing here is called the estimated standard deviation of population proportion. Oh, sorry, of sample proportions. We have only sample. That makes sense, isn't it? Because the error it's important to know the error by finding the critical value, the borderline, where it separates significant values from non-significant. And it's being multiplied to the estimated standard deviation. How far does it deviate from the mean? Right? So that information is also there. And so together, it helps us to find the margin of error for proportions. This is all for proportions. Right? I want to go back here and say for proportions. That's because we also have margin of error that we will calculate for mean, right? If you're interested in measuring the mean. Here we're interested in measuring the proportion, and so we are using it. So here's the question. It says, construct a confidence interval, so Ci, used to estimate a population proportion P. Okay. So this is what we're trying to do. For that, we need to first understand all these symbols. Okay, so let's write it one more time, what they represent, what they stand for. Excuse me, what they stand for. P is, remember P with no hat or prime, that means it's to do with population. I can't insist enough on how important it is for you to remember these symbols. Population proportion. P hat would be sample proportion. N, N, small n. It's all about sample, right? We don't know the information on the population. So small n will be the number of sample values or the sample size. And E or ME, right, is called the margin of error. For the purpose of uniformity, I'm going to just stick to P hat and E. If in your homework you find it as P prime and ME, please adapt to it. Z alpha over 2, Z alpha over 2 is the critical value. Now that we have all our notations in place, we should be able to construct the interval. So to construct the interval, we need all these values, right? We need all the information from here. We will not know this, of course. We will not know this. It is to kind of know what that value could be, in what range could that be in. That is what we're trying to find. So P is the only one that is unknown, of course, because it's to do with population. All others, we will try to determine them. Okay? Because this is to do with proportion, right? Think proportion as, for instance, if I said 60%, or we could use that for Facebook example, right? 43%. What was the example? I almost forgot. So it was the Gallup poll, right? It said these adults were surveyed, and 43% of the surveyed said that they have a Facebook page. So 43% has Facebook page. If you can think of that as the success of your study, right? So the failure would be the remaining folks who do not have a Facebook Facebook page. So the remaining would be what? 100% minus the 43%, right? So that would be the 57% who do not have a Facebook page. So you can think of 43% as success and 57% as failure, right? So when you think of success, failure, there are only two outcomes, right? If it's not a success, it's a failure. Therefore, we are going to call upon binomial distribution. Binomial, bi means two. There are only two outcomes, success or failure. So that is a connection we're going to make. So you can see how nicely we are able to connect actually normal distribution in the formula, but we're going to use the binomial properties. So we have some requirements that you have to fulfill. You have to make sure it's fulfilled in order to even construct the interval. Otherwise, your interval would not stand the test. So I'll just say requirements. For confidence interval, for estimating population proportion P. Okay, please understand that we will have another setup for population mean. So this is for population proportion. So I keep mentioning that in all these places. All right, one, when you choose a sample, that sample must be a simple random sample, right? If you had bias, if you did not collect your data properly, you cannot use it, it's useless. You cannot really salvage it. So that is an important requirement. The sample is a simple random sample. This was discussed in early lessons, right, in the beginning. SRS is the shortcut for it. So when I say SRS, I mean simple random sample. Okay. So every there was an equally likely chance for every member to be selected into the sample, right? Two, the conditions of the binomial distribution are satisfied. We must make sure that these are satisfied. If you go back to that, there were actually four underlying conditions that had to be satisfied. Okay, so one was you had to have fixed number of trials. Two, the trials were independent. This is from a binomial lesson, okay? So you can go back and check there. And there were two outcomes only. Success, failure, yes, no, true, false. So you can only have two. So in general, we just call them success and failure. Anything can be. So, you fail something, and if that is what you're trying to study, that is your success in that study, right? So you have to kind of keep something uniform. So we just call it success or failure. What you're after in that study is your success. And that is how we define success. Okay? And then the fourth condition was the probability remains constant for each trial. Probability of success. If the probability of success remains constant, correspondingly, the probability of failure, right, which is 1 minus the probability of success, will also remain constant. The probability of success remains constant for each trial. So those were the conditions of distribution, binomial distribution that must be satisfied. And third was that there are at least 5 successes and at least 5 failures. Okay. This is like minimum guarantee. You need to have these for this to even work. So if you had these three requirements satisfied, then you can proceed to construct your confidence interval. Okay. So here we go. This is how your confidence interval will look. Okay. Confidence interval for proportion is p hat minus the error, margin of error, this side, and p hat plus margin of error on that side. And your p, which is the population proportion, will lie in between those two values. Okay. And we found, we used the formula, remember? E is z alpha over 2 square root of p hat q hat over n. Okay. Remember, q hat is 1 minus p hat. So technically, if you had p hat, you got your q hat. The confidence interval, this is in the inequality notation, right? So you can write the confidence interval in an interval notation. So p hat minus e, comma p hat plus e. So if my interval was, say, 4 to 7, then the 4 that I have, say, 4 to 7, the 4 itself is p hat minus e, and the 7 itself is p hat plus e. Okay? And we'll tell you how to find the e if you were given the interval and all that. So we'll go back to that Facebook example. So I'm going to kind of add to you, okay, to that example. So Facebook example. So the Gallup poll of 1487 adults, right? This was the sample. We were interested in all the adults using Facebook, but we took a sample, showed that 43% of the respondents of the survey, of course, have Facebook pages, FB pages. Okay. And they're also giving us the sample results, okay? Because you have the sample, you went after 1487 adults and you collected their answers, right? So when you collected their answers, you got, you can find out how many answered yes, meaning they had a Facebook page, divided by the total number of people who participated in it, right? So the sample results are n equals 1487, of course, right? That's all the people who were sampled. And p hat comes out to be 0.43. They gave us 43%, so p hat is 0.43. The question says, find the margin of error, E, that corresponds to a 95% confidence interval. There are two more parts to it, so we'll do one by one, otherwise we'll have to come back and see what we wrote. Okay? So let's do that. Even if there was only one part, right? We have three parts, but even if there was only one part, we still have to do the requirement check. Otherwise, we can't proceed with it, okay? So, and we have to do the requirement check for, before we begin the problem itself, right? So don't think about it midway and then, because what if the requirements didn't match at all? Then all your work would be wasted. You have to go back and see what the requirement check was. The first one said it must be simple random sample. Do we have proof that the sample collected was collected by the simple random sampling method? Well, we know that Gallup organization is a well-known organization, and they are reputable. So we know that they're polling methods. Polling methods used by, now if you don't have that information, you're not sure if you can rely on it, you have to do that background check. You have to do that research to see how they collected their data. Okay? So used by Gallup, uses simple random samples. So we're good there. Okay. But again, for the sake of the purpose of this problem, we are using information we are given instead of researching it. We're told it's a Gallup organization that did this poll, the survey, so we're happy with that. We're okay with that. Okay. So the second one is about binomial conditions. So then go for all the 4 conditions. Okay, fixed number of trials. Yes, n is 1487. That's fixed. It's a fixed number. Are they independent? Yes, right, because one person's response does not affect the other person's response. The probability of their, the chance of their response does not depend on these previous respondents. So it is independent. So that is a check, that's a check. The third one is 2 outcomes. What are the 2 outcomes? FB page or no FB page. These are the 2 outcomes. So we got that as well. Nothing else was the focus of this survey. We got those 2. And 4, the probability remains constant because probability of having a Facebook page is fixed for a given point in time. Right? So I'll just say constant. So it's not like, you know, once you create a page, you have that page. Right? So the probability of having a page is fixed. It's not fluctuating, it's not changing, it's not subjective. So you are able to keep it fixed there for a certain period of time. So we've got that. So binomial conditions, all 4 satisfied. There was the third condition that, I almost forgot the third condition. There are at least 5 successes and at least 5 failures. So let's go to that. So we have 43% who responded, isn't it? So do a little math there to see how many, this is the percentage, right? How many out of the 1487 would be the persons who responded having a Facebook page. So, okay, here we go. This is the percentage of 1487. So do the math there. Right? 0.43 times 1487. Okay. So I have my calculator beside me. You should also do that so that you can quickly check. And you can also pause, but if you check this, this comes out to be 639.41. Okay. So kind of round it to 639 because the number of people who had Facebook page. So 639. So you know that the number of Facebook pages, number of people with Facebook pages, okay. Now remember, this is your success, right? Let me also mark that. 43% is percentage of those with FB pages. Having FB page is the success. Not having FB page would be failure, right? The number of FB pages is the success, which is 639, right? So if you are talking about p hat, it is 639 out of 1487, because p hat is the probability of success here. So q hat, for which you have to do 1487, the remaining folks, right? those were the ones who did not have an FP page. So you have to do the subtraction. It's 848. Yeah. And if you again did this fraction, you're going to get 0.43 here, right? And then you're going to get 0.57 there. So let me quickly again point to this as the probability of success. And this is the probability of failure. All that is good, but let's stay focused on the third condition, which said the number of successes must be 5 or more. Must be at least 5, right? That's what it meant. The number of successes is 639, which is way more than 5, so we got that good. And the number of failures must also be at least 5, which means 5 or more. So 848 is also greater than 5. So all of these conditions have been satisfied completely. Okay. So then you could use technology to do the calculations. We could do it manually here. Okay. So now we're ready to answer question A. Question A says the margin of error, find the margin of error, right? So margin of error. Now you have the formula. So your formula is E equals Z alpha over 2 square root of P hat Q hat over N. And let's collect all these details, okay? So let's quickly go back to the problem. So A says, find the margin of error E that corresponds to a 95% confidence interval. So your confidence interval is 95%. So to find Z alpha over 2, you can use that process we did to find that, or you could go to the table. Where was that table? Right here. So the table for 95% confidence level, the critical value Z alpha over 2 is 1.96. So I'm going to use this information right from here. .96. Okay. P hat, we want to use the decimal because that was given in the problem, so it's easier to keep it that way. The Q hat, it'll be 57%, which is 0.57. And then we need N to plug in the formula, which is 1487. Okay, plug those all in. You get 1.96, 0.43 times 0.57 divided by N, which is 1487. Okay. Calculate all this, and then you get 0.025166. That is your margin of error. So if you were trying to look at percentage, then that will be like 2.5%, right? 2.5% error. Okay, part B says construct the confidence level. I'm sorry, I was looking at something else. One moment. I'm sure they asked us to construct a confidence. Find the 95% confidence interval. So I'm going to erase this. Find the 95% confidence interval estimate of the population proportion P. Again, look at the language. They're asking for confidence interval, CI, right? Confidence interval estimate. Confidence interval should trigger to you that you're talking about this interval, right? And if you go back, we saw that interval was p hat minus e, comma p hat plus e. This was a shortcut, the interval notation for it. But if you wrote it in the mathematical inequality notation, it was p hat minus e less than p hat plus e. Again, please be aware of what your assignment wants you to do, how it wants you to present, and present it accordingly. So for our interval calculation, we need p hat and e. P hat is 0.43, right? That's in the problem. We just found e to be that big number. Keep it as it is. If they asked you to round it, then you can round it accordingly. So p hat and e are these. So I'm going to put it in the interval, in the inequality notation. So 0.43 minus 0.02516636 less than p less than 0.43 plus 0.02516636. And that simplifies, and then we can round it to 3 decimal places. Comes out to be 0.405 less than p less than 0.455. Recall this was the opening example I gave you on how to interpret the answer correctly. That was based on this problem. All right, so we found the interval. Okay. If you want to put it in the interval notation, of course, it'll be 0.405, comma 0.455. Interval notation. Then we go for the third question. Third one is kind of lengthy because it's asking us to kind of provide a background report on this. It says, based on the results, can we safely conclude that fewer than 50% of adults have FB pages? Based on the results, can we safely conclude that fewer than 50% of adults have FB pages? That's a question. And then they're asking you to write a brief statement. Okay. That accurately describes the results, meaning they're asking you to interpret it, right? That accurately describes the results. Okay. So think about this. In part B, right, we got the confidence interval to give us 0.405 to 0.455, right? That interval is, so if you go back to how we interpreted the interval, confidence interval, we said we are 95% confident that the population proportion will actually, that the interval, sorry, we are 95% confident that this interval, 0.405 to 0.455, will actually contain the true population proportion. So we said that this interval will contain the population proportion with a 95% confidence. So this interval, if you change it to percentage, right? We're reasoning out here. I'm not writing any statement here yet. 0.405 to 0.455. If you were to round this to percentages, you can say that this was 40.5% and this was 45.5%. So your P lies in this interval, right? So your 50 is far away. So your P is going to lie in here with a 95% confidence. So that means this is below the 50% mark. So it's fewer than the 50%. So because it's completely below 50%, you can say that, you know, the interval, it does appear that fewer than 50% of adults have a Facebook page. Okay? We can use the, so we can safely conclude that fewer than 50% of adults have FB page. And for that, this will be your reasoning that your confidence interval itself has the interval values below 50%. What about the statement, the summary, the brief statement regarding the results? I'm not going to write it here. It's going to get wordy. So I'm just going to explain it to you. Okay. So the percentage is based on a Gallup poll of 1,487 randomly selected adults in the United States. Okay. So the 43% of adults have Facebook pages. That information is based on the Gallup poll. In theory, 95% of such polls, the percentage should differ by no more than 2.5 percentage points in either direction from the percentage that would be found by interviewing all adults. So this is how you will present your report. But I'm just going to provide the pertinent details here. Okay. So they made a general statement that 43% of adults have FB pages. Okay. This was for all adults. This projection was for all adults. But Gallup took a survey of 1,487 people, and this was a randomly selected number of adults in the US. And so based on this survey, which was a sample, based on this sample, theoretically, we say 95% of such polls. Remember, we said that this was a process that in the long run would keep this interval true. So 95% of such polls, that in 95% of such polls, the percentage, right? In this case, the proportion. Should differ no more than, when you say differ, remember the margin of error. So you don't use the technical language when you provide a summary. You're not saying the margin of error should be, but you are saying that it should differ no more than 2.5 percentage points. Where did we get this number from? That comes from your margin of error. So let's go back to part A. And then I come back here and say, okay, margin of error, if you wrote this as a percentage, it will be 2.5 percentage, right? The 2.5 percentage points is the margin of error, which says that it should differ no more than. So it's a maximum possible error, maximum likely error. So I want to come back here and say, this information is your margin of error. So it's either direction, right? Up or down. Okay. If we were to find, if we were to interview all adults, okay. So it should differ no more than 2.5 percentage points, up or down, in either direction, from the percentage from the percentage that would be found if we were to interview all the adults. You get a percentage, right? A proportion. That proportion could be 43% itself, or it could be 44%, because that is going to still be in that interval that we gave. It could be 42%. So what we're saying is, well, it can be any of these because we are kind of covering us, the margin of error by saying you can go up or down 2.5% from whatever the proportion would have been if we were to interview all adults, from the percentage that would have been found if we were to interview all adults. Okay, so when you write the report, you have to flesh it out a little bit, but don't go too beyond, you know, the scope of your findings. Also, don't make it, you know, the wording should not be statistical jargon, but it should be something that explains what it means. So it really helps you to understand and interpret what you found. So it's one thing to find margin of error because it's just plug and chug. It's really more important to be able to interpret what this means. So this example helps us with that. Okay. So what would you do if you were to find the point estimate and E from a confidence interval? Okay. So if I gave you the confidence interval, can you find P hat and can you find E from it? That's the question, okay? So I'll just say finding point estimate is P hat, right? And margin of error from confidence interval. So here's the formula. Let's write the formula first, okay? Point estimate of P. P hat can be found by doing the upper confidence interval limit plus the lower confidence interval limit. This is very intuitive actually, divided by 2, okay? And then the margin of error is capital E. That's the upper confidence interval limit minus the lower confidence interval limit divided by 2, okay? So I'll just give you an example here, okay? So let's say this was about smokers and how this is from a real study, okay, this information. So the Journal of American Medical Association says that of the 71%, of the 71 subjects, so I'll just write the pertinent details of the problem. Of the 71 subjects, 70% were abstinent from smoking at 8 weeks. This is what the journal reported, okay? So this is, at 8 weeks. Yes, I shouldn't talk when I'm writing. Okay, so let me just read this for you. Of the 71 subjects, 70% were abstinent from smoking at 8 weeks. And in parentheses, they give the confidence interval, 95% confidence interval, 58% to 81%. They give this. So then the question says, use the statement to find the point estimate P hat and the margin of error E. So use the statement to find p hat and e. All right, so now we have to kind of use the information and build what we have. What we have, though, as given information is the interval is 58% to 81%. So let me write that out here. 58% to 81% implies that your P, the population proportion that you're really interested in, is between 0.58 and 0.81. Please write your percentage in decimals. Okay, that's coming from the question, and this was at 95% confidence level interval. Okay. So p hat is definitely the value that's midway between the upper and the lower limit. So use the formula. P hat is the upper limit, so 0.81 plus the lower limit 0.58 divided by 2, which is 0.695. And then your margin of error is upper limit 0.81 minus the lower limit 0.58 divided by 2, which is 0.115. Right? So this is the reverse of what we just did. In the previous problem, we found p hat and we found e, and we assembled them together as p hat minus e and p hat plus e. Here you're given in the interval format, and you're asked to separately find out what p hat and e would be, and it's a breeze because the formula is very, very basic, super simple. Okay. And then we have one more part, which is to determine sample size. Determining sample size. Remember again, sample size is your n, isn't it? So for this interval again to be robust, we need to have good sampling procedures, right? Definitely. Then we should have a reliable, a standard set confidence level, like 95%, 90%, and so on. And then we should have a good point estimate. And all these things will work if you had all these things, but you had very few people that you interviewed or surveyed. That would make it all go bad. So we need to know that we have a good minimum reliable sample size for us to even conduct this experiment or to collect the survey or obtain this sample, right? So your procedures may all be right, but you should also have the right number of participants in that sample, right number of values in that sample, okay? All right, so again, we already had this formula, right? This is, you need the margin of error, of course. So we saw that E is Z alpha over 2 square root of P hat Q hat over N. And this is what we're going to use to get N by itself. We're going to use mathematical procedure to solve for N. So then what we do is, of course, I want to write this one more time. We want to square both sides so that the square root can be removed and we can actually have, or we can actually access N. So mathematically, this is what we do, right? To solve for N. So you have E squared equals Z alpha over 2. That is also squared. And the square root and the square, right? It comes out as P hat Q hat over N. They're all positive quantities, so you don't have to put the absolute value, which you would do in a math problem. But here, they're all positive quantities. Your probability cannot be negative. The number of sample values, your N, cannot be negative. So we're fine. We got them all. We got that. One more step, you need to multiply. You need to get N by itself. Again, I will save all the math background stuff. So I technically interchange the N and the E squared. So I have N equals Z alpha over 2 whole squared p hat q hat over e squared. I just, because the mathematical steps would require you to get n on the left and move the e squared to the right. And so I just interchanged n and e squared because they were all being multiplied. You can't just do that every time. Because of the setup, they were all being multiplied. It was a quick move for us. So we got this. Now this is all good, provided you knew what p hat was, okay? When p hat is known. Because you don't have your sample yet. So how would you find p hat, right? So for practical purposes, you may not have the p hat. But if you found it to be an estimate provided somewhere else, you could use that. But for finding n and the number of people in your survey or the sample size, you may have a condition where you did not know what p hat is. We have a backup for that as well. So we're saying just multiply by 0.25 if you did not have p hat. So when p hat is unknown. So the p hat q hat is replaced by 0.25. Okay. And as always, when you have to round them, always round it up. Okay. So if you got sample size to be 757.3, round it up. Even though 0.3 would round down, you want to round it up because you're always safer with one more than one less, right? So you just make it as 758 instead of 757. Okay, so we'll wind up with this last problem that helps us to answer these or find determine. Okay. So I'll just read the story and then we'll just fixate on just the problem, because these problems are word problems, they're wordy, and it'll be too much time to just write out the problem. So it says, when the author was conducting research for this chapter, he could find no information about the percentage of adults who make online purchases. Yet that information is extremely important to online stores as well as brick and mortar stores. If the author were to conduct his own survey, how many adults must be surveyed in order to be 95% confident that the sample percentage is an error by no more than 3 percentage points? Okay. So I will come over here. So this is about the overarching theme is what percentage of adults make online purchases? Okay. Before that, we're saying the question is, how many adults must be surveyed in order to be 95% confident that the sample percentage, remember the language, sample percentage actually refers to the sample proportion. Because we're interpreting this in real world context, the word percentage is more used than proportion. Proportion is more a math term. Math folks can understand that better than common users. That sample percentage is in error by no more than 3 percentage points. Okay, that's all they've given us, okay? So we have 2 parts here. Assume that a recent poll showed that 80%, you don't have that information, but you are looking around and you found that a recent poll gave a sample proportion that 80% of adults make a point estimate, I mean, make online purchases. Then B is that assume we had no prior information. On this point estimate. So we have these two conditions. So in both these cases, we're asked to find how many adults to be surveyed, right? That language, how many adults must be surveyed, means we have to find N. Okay? Let's collect all the details we have. So for part A, with 95% confidence level, we know that alpha is 0.05, which means your Z alpha over 2 from the table or from your, if you're interested in doing a calculation from scratch, you can do that. Well, it comes out to be 1.96. And the margin of error, is that given to us? It is given to us, but it's all written in words. The margin of error is no more than 3 percentage points. So E is 3%, or we don't write it as percentage, we don't use it as percentage in calculations, so it is 0.03. So E is also given to us, 0.03. For part A, right, we are told that in a recent poll, there was 80%, it showed that 80% of adults made online purchases. So P hat is 0.80 or 0.8. If P hat is 0.8, it implies Q hat is 0.2. 80%, the remaining is 20%. Right? 1 minus P hat. All right, we have enough details to assemble our values into the N formula. So let's write the formula one more time. Z alpha over 2, because writing the formula correctly is doing it half right? E squared. Now plug in all the values you have. 1.96 is squared. 0.80 times 0.20 divided by 0.03 squared, which is 682.951. And that comes up, again, round it up, 683. Even if it was not a 0.95, it was a 0.1, you will still round it up. We're always better off rounding up than down. So then we say, we must obtain, we meaning the author, right? That was the question. He must obtain a simple random sample that includes at least 683 adults, right? That was for part A. If it's part B, then we use the same details, but then we do not know the P, right? P hat is unknown because we are told that there was no prior information, which implies Q hat is also unknown. So we adapt to the other formula, which says N is Z alpha over 2, the whole squared, times 0.25 divided by E squared. So your Z alpha over 2 will still be 1.96 whole squared times 0.25 divided by E, which was 0.033%. And that gives us 1067.11. You can pause the video, calculate it, please. Have the practice yourself. 1068 when you round it up. Look at this. Here we had a 0.11, we had to round it up. When you do not know and you don't have any prior information, look at how quickly the N increases. Okay, it's almost double, right? So n is 683 there if your p hat was known, but here it is 1068 because you are trying to be more conservative in providing that information. So we need to obtain a simple random sample that includes, always interpret your answer so you understand what it means. At least 1068 adults. The more, the better, okay? This is the minimum. So if you want to do 2,000 adults, really good, because then you have really expanded the minimum requirement, and you can be assured that you will provide reliable information because your sample size was larger, all right? So I think we kind of covered all that we needed to in this section. But chapter 8 is not done yet. This is only part 1 of it. And I will meet you in part 2. And with that, we'll be done with chapter 8. Thank you again. I hope you enjoyed the video. I will see you in the next one.